Hamilton's principle says, of course, that the action is minimized for physical trajectories. And some of the things I called Lagrangians, just in what I was just talking about, were they kinetic energy minus potential energy? They were not, right? I was just looking at like the length function or something. Or for the Snell's law, it was time that we had integral which described the time of the light path travel. So you see, variational calculus, when I say Lagrangian in the sense of variational calculus, L does not have to be kinetic energy minus potential energy. But when we apply it to the problem of classical mechanics, it's kinetic energy minus potential energy. So beware of my usage of the word Lagrangian. It means different things in different places. Here's one that's relatively simple. The projectile motion. So this is just like three-dimensional, like this. So ignoring friction and using z as the vertical direction, you have the markers essentially free. I'm ignoring the rotational degrees of freedom of the marker around its axis, just thinking of it as like a point particle. So the kinetic energy is just 1/2 m x dot squared plus y dot squared plus z dot squared. And then we have minus mgz because the potential energy due to gravity is just mgz, putting z equal to 0 as the floor in here, let's say. Euler-Lagrange equations give you that x momentum and y momentum are conserved. And on the other hand, the z momentum is changing at the rate of minus mg. Of course, that is just the standard set of Newton's equations. And if you integrate them, you get the kinetic, the equations of kinematics that we perhaps recognize from Physics 231. Now, here's one that's more interesting, a simple pendulum. Now, one of the problems I asked you guys to do in the quiz was a double pendulum. All right? So to set up the double pendulum, what do you got to do? You have to identify where is there kinetic energy in the problem, and what is the potential energy of the problem. We have to think of it as a system. All right? So we could look at this one, but what I wanted to do today, and I may still have time, it's debatable. I think we're going to get it. I think we'll be able to get it. Let's try. Is I wanted to set up something that's kind of like your homework problem, but a little bit weirder, which would be, instead of a double pendulum, how about a pendulum with a spring? What if we had a pendulum, here's a mass, m1, and then a spring in a mass m2. And this spring can, has spring constant k. It can go any different which way it likes. Then set up equations of motion for it. How would we do that? So I'm assuming, of course, that I'm assuming that this is like a light, thin rod, that it essentially can't flex. And it's going to be useful for us to define an angle, say theta 1 here. And it's probably going to be useful for us to define an angle theta 2 here, if I had to guess. So in terms of kinetic energy, what are the kinetic energies of this problem? I think we have 1/2 m1 v1 squared, right? Plus 1/2 m2 v2 squared, where v1 and v2 are respectively the speeds of mass 1 and mass 2. So if we were to use coordinates, well, that's always a question with one of these kind of problems is, what kind of coordinates should you use? Well, I needed to tell you the length of the pendulum, too. I haven't told you that, right? It's a bad habit I've gotten into recently. I gave a L, let's say. So I think V1 squared is really just what? V1 is really just what? L theta dot, theta 1 dot, isn't it? Because it's just depending on how that angle is changing, it's just got the radial velocity because we're fixing the distance from the pivot point to M1 to be L. Yep. This is in a plane, right? Yeah, this is in a vertical plane. Yeah, not three-dimensional. So I've been inspired by the book I'm teaching 201 from. There's essentially no three-dimensional physics in this 201 book. So I'm starting to think physics is just two-dimensional, and not really. So offensive, this book. Anyway, V1 L theta 1 dot. That should be the kinetic energy associated with M1 should just be that, right? So, excuse me, 1/2 M1 L squared theta 1 dot, yeah? Squared. And how about V2? Let me suggest that we invent a system of coordinates based on M1 as the origin. And I suggest we say that M2 is at where? Well, I got to be careful. So where is M1? It's at x equal to where? Well, let's put the origin up here just to be. Careful. So I would say that x is equal to, looks to me like L sine theta 1, yeah? And maybe I should call this x1. What's y1 equal to? Looks like minus L cosine theta 1, yeah? What about M2? Well, it seems to me that the distance, let's say the stretched distance, what do you want to call it? S? I like that. It's good. And so I'm imagining that if S was equal to 0, then M1 and M2 are just right up next to each other. All right, so M1 is literally distance M2 from M1. So S is both the stretched distance and the distance between the masses. And so M2, where is it at? Yeah, what's x2 equal to? And what's y2 equal to? I'll get you started. L sine theta 1. That's where that's where we start from, and then we have to do what? Plus what? Yeah, just plus. We'll use the convention that theta 2 as pictured is negative. Theta 2 as pictured is negative because that would make these formulas make sense up here. If theta, this is positive theta, and this is negative theta over here, then these formulas make sense. Like sine theta would be positive to the right and be negative to the left. So we want that convention. And likewise for theta 2. As pictured, theta 2 is negative. So I would say OS, right? Sine theta 2, yeah? And, oh yeah, minus L cosine theta 1. Yes, minus S cosine theta 2. Of course, I think the smarter thing to do here, I mean, yes, you could say that V2 squared, we could say V2 squared is x2 dot squared, right, plus y2 dot squared. Fair enough. But wouldn't it be, oh, I guess I need to actually work that out. prediction. This works out to L squared. Oh, I shouldn't predict. I don't know. I guess I actually need to work it out. I mean, so this, something pretty should happen though, I think. What's x2 dot squared? It's what? L cosine theta 1 dot plus s dot sine theta 2 plus s cosine theta 2 dot squared plus, likewise for the second one, minus, well, plus L sine theta 1 dot minus s dot cosine theta 2 plus s sine theta 2 dot square that. That would give me the velocity of the second mass as a function of theta 1 and theta 2, as well as the stretched length of the spring. So I probably don't have time to work that out. Let's focus on my remaining extra minute of how would you set up the potential energy. So if we put minus m1g, well, let's say it this way, m1gy1 plus m2gy2 plus 1/2 k s squared. That would be the potential energy. Because you have the gravitational potential of the first mass, gravitational potential of the second mass. Both of those y's are negative, and they're here. And the s squared is the potential energy of the spring. And then to construct the Lagrangian, we take that kinetic energy. Take that kinetic energy minus that potential energy, and that would give it to you. The problem I gave you is the double pendulum, which is nicer than this. But the setup is very similar to what I'm doing. So next class, I'll do two things. I'll describe to you the method of Lagrange multipliers for variational calculus, which is really, really neat. I don't think I've assigned you any homework on that, so shame on me. And then we'll take the rest of the time to review for the final. Sound good? Course evals. Oh, course evals. Talk about course evals. When you take the course evaluation, the key point I would make to you is that mathematics is truth. And who is the author of all truth? Who is the author of all truth? You know the answer to this. So when you answer the question on the course evaluations, was there biblical integration? To say otherwise, to mark anything but strongly agree, is to indicate that you believe that mathematics is not part of God's truth. Do you want to be that person? You don't want to be that person. Ian's not here. Oh well. Also, I will be giving you cookies on Tuesday, so keep that in mind as you do the course evaluations. So anyway, they could be chocolate chip. Yes, you can put in orders if you'd like. What's that? Homemade ones? It depends on whether my wife is feeling up to it. We have sick kids, so it's I'm not sure. Oh, I thought. Oh, by the way, lest I forget, if you want to read more about variational calculus and like a lot of fun stuff, this is Emmy Noether's wonderful theorem by Neuenschwander. And I had a student, electrical engineer, use this book for an honors thesis a couple of years ago, and it worked out really well for him. It's got, basically how you can look at Maxwell's equations from a variational principle, everything else. It's a very nice little book with a lot more physical justification than I've been giving you. So anyway, on the other hand, I've given you more actual examples, so whatever. Did you already cut it off, Grace? Or?